Good morning. First of all, thank you very much for the organizers for the invitation. I'm a bit out of place, not out of place, but I'm feeling different because I'm not from agronomy, from biology, I'm from computer science. I believe I'm the only one who's not from biological science here, but I'm trying to speak the correct jargon and the right words in biology science or in agricultural science. So what I do in this talk is, first of all, I have to acknowledge some people, some colleagues who helped me all this work for the last years. And I'll try to make the connection between big data, data science, artificial intelligence, go into the direction of machine learning. And in the end, I'll show a little bit of some works using these techniques for in agriculture. So when I started working machine learning, it was very difficult to find data. I had to fight for data. People had the data, didn't want to lend the data to anyone. Now it's the opposite. Have too much data, it's difficult to choose which data we're going to use in experiments from someone who works in machine learning, for example. And in particular, in plant breeding, this is the graph which shows the increase of the number of data and the prediction until 2034. So you see from now to 2034, the amount of data will increase by almost 10 times. So what's happening is you are getting an information overloading. So there is this nice graph from Ryan Lew's theory of too much information, which shows the amount of information since the Paleolithic art, right, is increasing very slowly with the writing, with the printing, with the electronic media, even with the internet, but now it surpasses our capacity. It's much more than you can absorb, much more than you can process. So it's not that you, in the past you knew everything about everything. It's that in the past at least we knew what was going on. Now, not even what's going on you know. So you need some support to help us and to try to overcome this kind of information overload. This is not a graph which shows how too much information, instead of being good, is bad for our decision-making process, right? So there is a point where if you have too much information, have more information, instead of increase understanding, it decreases understanding and harm our decision-making. So this is what's behind the idea of big data. And is big data a new thing? In the context you understand now, is a new thing. But this word big data appeared many times before with different meanings. For example, it appeared in 1998, but the context was the amount of facts, not the amount of data. It's from the people in social science. And then we had again in 1990, and the context now was, the amount of bits, not of facts. And then the meaning which was closer to what we understand today was in 1997, but it was related to visualization techniques. And if you ask now anyone, what is big data? Each person have a different understanding of what is big data. There was a recent survey which asked 40 people who are leaders in big data what they understand by big data. And we had all different kinds of definitions, like data that are too big for traditional data process techniques, which are intuitive, and then data that need new processing techniques, then very complex data, very complicated data from different formats, different sources. Data that are important, doesn't matter if they are big or complex, but they are important. And the charge opportunities that come with the new age of data, right? So the possibility that you have as new data become available. So even if you work as a cloud of words that we people from computer science like very much to do, depending on which text, which paper do you have access to, you have different words that appear as important for big data. But what you have is, there's kind of consensus that, at least in the beginning, that big data could be defined by 3 V's: variety, velocity, and volume. Volume, both for structured data, with kind of a Excel file or tabular file, unstructured data like DNA, for example, RNA, or a sequence of amino acids in a protein. Variety, data come from different sources with different complexity, different formats, and you have to integrate them. And velocity, data comes faster and faster. And you have to do it. sometimes you have to have model that can forget about previous data because that probability distribution that generate the data can change along the time. So this is how the, in 3 dimensions, the thing evolved in the last years. When I started working with computer science, the velocity was very low. The data was produced in batch. So I have one data now, some files later. And then now you have the data stream where data comes at high velocity. Regarding volume, we start with megabytes. Now we're talking about petabytes and so on. There are even prontobytes. And for variety, we start with tables and move to database. And now get data from sensors, from social media, and so on. Please, if you have any questions, feel free to interrupt me anytime. Just raise your hand and ask a question. So these are the initial 3 Vs. Then someone suggests a study to see the importance of each V in each kind of each branch, each kind of economic sector. And you can see that we have different importance for banking, for communication, for education, where the importance can vary from very low to very high. But I think what concerns us here is manufacturing commodities. So this is a particular area on everything. Volume, velocity, and variety is very important. Mainly velocity and volume, but also have a big variety. So this is the thing what happens in agricultural data. But then people start increasing data. Then 4th data, 5th, increase the number of Vs. And now we have something like 10 Vs. And there is even some joke that people say there are 42 Vs. And there's a study which predicts that by 2021, we have like something like 120 Vs to define big data. Right, but in spite of the size of the data, you can have very important information, very rich information inside the data. And for that, you have to analyze this data, because once you analyze the data, you have several benefits, not only economic, but social and political benefits as well. So because of this reason, there is increased interest in data analysis, analyze this data to collect useful and new information from the data. But this interest in data analysis is not recent. For a long time ago, people have had interest in analyzing data, even for food and farming. For example, if you go to Babylon 4,000 years before Christ, the people who take care of the kind of government, they are doing regular census to see how much food we need for the population of a particular region. And there's even some census records which are lay plates, and on the symbols in the left side means eat. And if you go 1,500 years later in Egypt, people all use census to decide how many people you need to build a pyramid and how you divide the land between the floods of the Nile River, right? So in Egypt, since 5,000 before Christ, you have this kind of analysis, data analysis to decide how you're going to produce food, for example. But all these analyses were made by humans. The analysis is still made by humans, but before they don't have any sophisticated tools. So it was difficult to do a widespread analysis because you didn't have enough experts. When you found one, the cost was very high. The situation is the same today. And now we have another difficulty, but because we have a large volume of data which are complex and come by high velocity, so this job is even more difficult. So you need some new tools to analyze data, and this is where data science comes, right? There are several progress in mathematics, statistical computer science, which provide us very sophisticated tool to improve our data analysis. So now we have many techniques for data science, right? People start to work with Excel, but now they have lots of very good techniques to try to extract new knowledge from data that are new, relevant, and useful. So the key question when you are with data science is, how can efficiently extract knowledge from a potentially very large data set which may come in stream? So the idea is you get data, you extract knowledge, and use this knowledge to make decisions. So now comes my first slide about trying to put the border between big data and data science. So what's the difference between them? The difference is very simple. Data science uses associated data modeling, extract knowledge from data. So, and big data is associated technologies that allow the use of data science techniques. So main technologies for data extraction, data storage, manage the data, transmit the data by IoT, for example, and process the data. So in the end, it provides the infrastructure needed for using data science. So data science is more data analysis, big data is more data collection. But big data, is the term big data new? No, it's not new. It appeared before, a long time before. Sorry, not big data, so data science. Isn't it new? No. In 1974, there's a very famous computer scientist who gave a course in the International Computer Science Conference called IMPB, where it gave the first definition of data science. The scientist was from Denmark. He didn't like the name computer science. In Denmark, you don't have computer science. You use datology for the computer science course. So you can do two new terms, datology, with the study of data, and data science. A similar thing happens in statistics as well. But later, in 2001, in parallel, a statistician called William Cleveland, he has defined what data science is and the importance of data science for the modern statistics. And how does data science associate with all the existing technologies or the existing techniques? The more related thing to data science is data mining. But data science is more than data mining. It has more steps than data mining. Includes things like data curation. So like you do in museums to curate art, for example, you have to curate the data to assure that the data has a reliable origin, for example. Planning of your experiments using statistical techniques. Data transformation, data preprocessing, data modeling, visualization, evaluation, and validation by domain experts. So every research you do in data science to validate what you have, at least from the computer scientist or data science point of view, you have to validate with someone which is a specialist in the data domain. For example, if I apply data science agriculture by myself, I need to work together with some people from agriculture to validate what I found in my experiments. So what is really data science? Data science is a combination of different areas like machine learning, data curation, as I mentioned before, data quality techniques, some descriptive statistics, pre-processing, statistical inference, scientific visualization, and many other areas. I'll just say a little bit about which one of these main processes of data science. One of them is very important, data quality. So most of the data that you use in experiments, they're not produced to be used by data science techniques. So you have problems, have quality problems. They estimate that at least 5% of the data has some problem. And if you have data with some problem, you cannot extract good models or trustful models. So the idea is garbage in, garbage out. So there are many techniques to improve the quality of the data, dealing with, for example, noise in the variables or in the target of the data, missing values, which is very common when the data is collected manually, redundancy of the data, and so on. Another important step, once you improve the quality of the data, is data pre-processing. There's a big problem called dimensional problem in data science, or dimensional course, where if you have too many variables associated with the number of objects, then all the objects become so close that modern techniques are based on distance, they have problem to discriminate the objects. So it's very common with a very large number of variables like in gene expression analysis to do some feature selection. And sometimes your volume data is so big that you cannot apply the data science techniques direct to the data. So you have to do some sampling as well. You have to get a sample of the data that preserve the same statistical distribution of the original data. Sometimes also, instead of some feature selection, we will select a set of variables, you can aggregate the features like you do in principal component analysis, for example. Other thing you have to do is, for example, you're doing classification regression, you did maybe imbalance, have too much data from one class, you need the others, or the data distribution for the regression is very imbalanced. So this also harm many modeling techniques. And finally, for many problems, the data is not in a tabular format, or some techniques they have some restriction, like they can only work with numerical data or with symbolical data. Need to do some data transformation. This is particularly true when you have molecular biology data, like DNA, RNA, or proteins, for example. Right, so here comes to my main interest in this talk, data modeling. I work in machine learning. My master and my PhD were neural networks, so I have been working machine learning for the last 30 years. And the idea of machine learning is trying to model the data. You have two approaches to create a model. You can have it process-driven, where you're trying to have a mathematical equation describing the process, or what's more common now is data-driven, where you use the data to create a model that explains the data. So this is the idea when you use statistics or artificial intelligence, try to get the data, and that's why it's important the quality of the data, because the model will be as good as the data you have. And on the other hand, you have to do the best you can do, the most you can do with the data that is available. Right, so let's talk a bit about artificial intelligence, because it's a key aspect of data modeling. There's a very good definition from many years ago, which say that it's a study of how to make computers to work like or better than people for some tasks. But there are other definitions though. Some people are not really glad with the name artificial intelligence. Artificial means that it's not intelligence, it's artificial. So many people provide different names, like machine intelligence is very much used today. Even Nature has a journal for machine intelligence now. Simulate intelligence, so simulate is different from artificial because I want to try to simulate intelligence now. It's not artificial that comes from nothing. And thinking machine. Thinking machine was a term proposed by Turing, Alan Turing, was a very famous mathematician, computer scientist. He proposed in 1950s. I'll go back to Turing later in my slides. Turing proposed a new approach to decide if a machine has or not intelligence. The approach called Turing test is have one person behind a wall, and on the other side of the wall, you have a computer and a person. And the person on the left side keep asking questions to both without knowing who is answering the questions. And the questions passed by text. If the person on the left side cannot distinguish the computer from the person, so the computer is said to be intelligent, have intelligent behavior. Now everything changed a lot. People are using videos now and other things. I don't know if you saw the film Ex Machina, which is about intelligence as well in a new era. And why artificial intelligence is important for agriculture, for example? There's a nice study from FAPESP from last year, which says for technology as a whole, not only for artificial intelligence, that every R1 you spend on research and development, higher education, or rural extension has returned. So it has happened for the state of São Paulo, 12 reais. And there's another study, now related to artificial intelligence, also from last year, from a Canadian news company, which says every $1 you invest in artificial intelligence, in good quality artificial intelligence, well done artificial intelligence, it can return $44. So if you put the two together, you see the benefits that artificial intelligence can bring to agriculture. And that's why I think the organization was they were very fortunate when they created the team of the third event. And as I explained what's data science, what's artificial intelligence. Artificial intelligence has many different areas, like machine learning, games, logic, planning, probabilistic reasoning, robotics, intelligent agents. And what it has in common with data science? Machine learning, right? Both work with machine learning. So that if you want to have a graph to describe, like a Venn diagram, describe the relation between artificial intelligence, big data science, you see that there's an interconnection between the three areas. So it's difficult to define what's the border between each pair of them. And if we go deeper, as I mentioned before, in artificial intelligence, we have one of the sub-areas is machine learning. It's the sub-area which is more in evidence today. So there are many people talking about machine learning and artificial intelligence. And in machine learning, you have a particular sub-area called neural networks. And in neural networks, you have another sub-area called deep learning, or deep networks, which are taught by deep learning algorithms. And if you put together part of data science, artificial intelligence, we have data science with machine learning, right? So as I mentioned before, a key aspect of artificial intelligence now and for data science is machine learning. I was at a conference last year, education conference, and it was like here. Everybody was from a different area. Everybody was from pedagogy, from education. And they asked me, what do I do? And I said, I teach machines, right? So that's what we do when we work with machine learning. We try to teach machines. And try to teach in a similar way as we teach humans, by providing data. So the idea of machine learning is relating from data to learn to extract what's relevant, what's new, what's useful from a data set. And all this information that's extracted from a data set is represented by a model. And there are very successful stories of use of machine learning, not only in agriculture, but several different areas. And mainly they divide the use in two applications, right? Descriptive task, where I try to describe the data, for example, using clustering techniques, and predictive task, where I try to predict something, like regression and classification. The thing is, there are several machine learning algorithms. There is estimated that say that there are tens of thousands of different machine learning algorithms, and hundreds more are created every year. And each one has some clever ideas about how to work. Some are generic, some are very specific for a particular application, and they all take different aspects into account. So when you apply machine learning for your data set, the quick question you have to ask, I'll put this question in the next slide, is which algorithms would I use for my data? So which algorithms should I use to have the best performance for my data set? I cannot try all the 10,000 of algorithms. It's hard to try even a few tens algorithms or a few hundred algorithms. And if I try all of them, I have to do it again for all the data, for a new data set, for example. Yes, you have to, because there is a very nice study called the selective problem or selective superiority problem, which says that each machine algorithm is good for a particular conformation of the data set. Each machine algorithm has a thing called bias, which gives preference to find some particular kinds of models. And the algorithm will be better for data set if the bias of the algorithm match the bias or the conformation of the data set. That's why even for the same application domain, I have data set for the same application but collected from different sources. If they have different conformations, the same machine algorithm can be good for data set and not good for another data, for the second data set. And is this bias a good thing? Yes. An algorithm cannot learn without a bias. And there are two main biases in machine learning algorithms. One is the search bias, how the algorithm looks for the function, for the hypothesis to model the data. And the representational bias, how the algorithm creates models and how these models represent the knowledge, right? Like language bias as well. And without bias, there is no learning. Without bias, you just memorize. And things get even more complicated. You not only have to select what's the best algorithm, but you have to fine-tune the algorithm. So as each algorithm has a set of hyperparameters. So what's the best value for the hyperparameters? But you all have all the other steps for data science, like input data quality, like cleaning the data preprocessing, and all of them have several alternatives. Even if you work with phenotypes, if you have the image, you have different ways to do image segmentation. So which image segmentation algorithm I'm going to use? What's the best suited for my particular image? Right? So we have lots of decisions to make. And we have more things. We have to take care of the implementation of the bugs and define all the pipeline. What's the sequence of steps to have a good solution using data science? This is what's called now end-to-end machine learning. So it's the whole process of modeling. It's not only the modeling, but the pre-process and the post-processing as well. So as I mentioned before, it's like you have several tabs, and you have to know how to find the best tuning for each tab to have the best performance, the best model in the end. And the bad thing is, they're not independent. So if you turn a tap to the left, one tap that was good becomes bad suddenly. So you have to find the best combination of opening in all the taps to get the best performance. It's an optimization problem. So you have to know how to modify the machine learning algorithm times, how to deal with oversampling or undersampling when you have imbalanced data sets, for example. One of the class in classification has less example than the other class. Sometimes you have to extract new features or recode the feature they're extracting before. Sometimes you have to do feature selection, feature aggregation. You have to tune the hyperparameters. You have to deal with missing values, with noise. You have to check for overfitting. You have to discover some bugs in your code, if you change the code, and many other things. And what's also the best pipeline, the best sequence of tasks to have the best model. So my question now becomes more complex. I not only have to select the best machine learning algorithm to have the best performance. I also have to know what's the best pre-process techniques, what's the best hyperparameter values, what's the best lots of other things. But I don't need to find the best. I need to find a good value, a good alternative. What's a good pre-process technique? What's a good machine learning algorithm? It's like the optimal is the enemy of the good, of the best, right? So I try to find a compromise. And also, what's the best pipeline of techniques to have a good performance? So it's kind of have a gap of artificial intelligence, data science, machine learning. And as I mentioned before, what I want the end, I want to have a good model. And as I mentioned before about data analysis, in data science, artificial intelligence, machine learning also have a lack of experts. There are several predictions, not only here in Brazil, but in US, in Europe, that the number of people are going to graduate in data science, machine learning, artificial intelligence is much smaller, and it becomes smaller than the demand for all different application areas. So how can you deal with this problem? How can you deal with this gap? There's an alternative. It's called AutoML. So AutoML could be a hype, but there are lots of interest recently, AutoML. So people say that is a way to democratize the use of artificial intelligence, data science, and machine learning. Is the new rise of machine learning, and so on. And this is why many companies, let's see here, like Google, Amazon, Apple, Microsoft, they have research groups who work with automated machine learning, with AutoML. So what's the idea of AutoML? It's automating the whole process of using machine learning from end to end. And it has two main goals. One is to provide support to non-experts, to at least have a good solution. Because like driving a Tesla car, you can have it totally autonomous, or you can also improve the productivity of the experts by reduce some manual work and speed up the time that's needed to develop the tool, a good data science tool. You can have there are several ways of automating machine learning. The three main approaches by optimization. Optimization means I can optimize the model, use optimization techniques for operational research, for example, optimization, combinatorial optimization, or I can create a new algorithm, particularly good for my data set, so I can combine different parts of the 10,000 of hundreds of algorithms to create a new one that's better for my data set, for my particular data set, and trying to avoid overfitting. So I create a new algorithm from scratch, or I can use, like Netflix, I can use recommendation. How can I use recommendation? Each data set, I can describe the data set by extract features called meta features, which I have to describe the data set, like how complex the data set is, for example, or some very simple statistical features. The way is to describe the data set. And then if I use machine learning for hundreds of data sets with different machine learning techniques, different pre-processing and so on, I have a metadata set with all of this previous experience. And I can use this data set as Netflix used the data set of people preference for movies to see, for a new data set, what's the best alternative for this particular data set. So I can recommend. I can not only recommend, I can run the techniques as well. So instead of only recommend the movie as Netflix, my techniques can recommend the movie, watch the movie, and say and tell you what the movie was about. And you can also combine both. You can combine optimization techniques and meta-learning, which is used for recommendation of techniques. You can do, for example, when I do some hyperparameter tuning, you have a high cost, computational cost, to find the best set of values. But I can use meta-learning to recommend where should I start the search for my hyperparameter values. Or for this particular data set, if I use the values, the default values recommended by a particular tool, they are enough. I don't need to tune the hyperparameter values. And then I can save lots of time in my experiments. So these are some tools that are available. There is even some competitions for what is the best AutoML tools. They run at least twice every year in different conferences on data science and machine learning, like NIPS, for example. We are doing a tool as well in São Carlos called Pagé. It's a tool for automating machine learning from end to end. The idea is to work with preprocessing, machine learning, post-processing, pipelining, and to be like a Lego tool that you can easily expand using public code, open code. Our main idea is to find what means responsible artificial intelligence, or responsible data science, or responsible machine learning. And one of the premises of a responsible use of data science is that your model should be interpretable. So there's a whole area called explainable AI. In Europe, for example, with the GDPR now, with a new regulation about using data, if you have a model that's created by using machine learning techniques, and this model is going to affect someone, the person has the right to know how the model makes decisions. Right? So this is a big challenge in techniques like neural networks, including deep networks, because usually they create black box models. But the good thing is there are several studies trying to explain the models created by deep networks, or neural networks in general. So it's a very active research area. Right, so let's go back to intelligence. I talk about intelligence associated with agriculture. The question about what's the value of intelligence has started many years ago. There's a British mathematician called Irving J. Good. He worked with Alan Turing break the codes of the Enigma machine in the Second World War. And they are good friends. They end up working in the same university of Manchester. And they very often talk about their concerns about the future of machine intelligence. Machine intelligence is how Turing used to define artificial intelligence, right? And they both are convinced that one day machines will be more intelligent than people. And this day is coming. But there are two ways to measure how machines are more intelligent. You can have local intelligence, where the machines are good for specific tasks, better than human for specific tasks, and global intelligence, where the machines, they substitute the human being. They can do everything we do. Well, I don't think that the second branch is going very far. At least there's no more interest in a global intelligence. Why do I need intelligence for? A global intelligence for? Most of the research are in local intelligence. Even the guy who created deep learning, Geoffrey Hinton, they asked him, what do you think of global intelligence? He said, what's it for? Even so, A.J. Good tried to estimate what the economic value of artificial intelligence, of an intelligent machine. And he used this benchmark, the brain of a very famous economist, Keynes, and he estimated the value of Keynes to the global economy as 100 billion pounds. And they estimate an intelligent machine could be worth 1 million times what Keynes would be worth. So like 1 mega Keynes. And this guy, he has lots of nice activities. He was, for example, the consultant to Kubrick's movie Odyssey, Space Odyssey, 2001. And he also wrote a text putting his concerns about the superhuman intelligence. And what said is, in the end, this ultra-intelligence machine can be our last invention, if it's a global intelligence machine. Because if machine is clever than us, why the machine need us? Because a machine that's very clever can design a machine that's even clever, even more clever, and so on, never ending. And they don't have the limitations that you have, the biological limitations that you have. So this gives you origin to the concern about autonomy and safety, right? So, as I mentioned before, different from us, the machine have no physical limitation. To see an example, just compare our eyes with the recent telescope. They can see much farther and much better, right? And the same for the microscope, for very small things. So there's a big concern in the artificial intelligence community about how can we coexist with these machines. There's a think tank in UK called Alan Turing Institute, and half the institute are people from exact science, like math, statistics, computer science, and another half are people from human science. And there are lots of research going on about lethal weapon machine, autonomous weapon machines. In the United Nations, there's a committee studying lethal weapon machine. There are two different views. One is the European view. We say that there should be some limit in these machines. They shouldn't be totally autonomous. And there's another view from US, say, no, they shouldn't have any limit. They should be completely autonomous. Well, but this concept of automation, they didn't start now. If you go back to Plato in 370, right, there's a dialogue, there's a book with a dialogue between a protagonist, Socrates, and Phaedrus, which is called Phaedrus. This book is about how you should use rhetoric. And he mentioned that writing is very dangerous, because if you stimulate the writing, it will take place of the human memory, so it's very dangerous for the humanity. And reading as well is very dangerous, because if people learn how to read, they will substitute true knowledge by mere data. So the problem is not the technology, it's how we use the technology. That's why there are some movements to stimulate a responsible use of data science, artificial intelligence, and machine learning. This particular one is Netherlands. They have for challenge like, you cannot have any prejudice when you use data science. There are some companies, health insurance for example, who say if you have some problem in the past, your insurance will be higher. It should not be allowed. Another thing is, data science should not be guesswork. You should be very careful about what data science is doing, and very sure about the model is working as it's supposed to be working. Another is regard privacy, right? So you have to be careful to not divulgate personal data. And transparency. It goes back to explainability, to interpretable model. So you should know what the model is doing, how the model is making decisions. Right, so then, in a whole, responsive data science is concerned with accountability. So who is in charge, who is responsible for the model if the model makes a mistake? For example, there's a big discussion about the autonomous cars. If the car kills someone, who is responsible? The manufacturer of the car, the manufacturer of the sensors of the car, people who bought the car, and so on. Another concerns about reproducibility. If people who are using data science machine learning have to make available the code, so allow the people to do what they did. Another one is about privacy. There's a recent experiment with data from Facebook. If you apply machine learning algorithm to 300 likes, the model can learn more about you than your husband and your wife. And if 20 likes, you know more about you than your colleagues. Another concern is transparency, as I mentioned before, so that's why there's a big interest in explainable AI. And fairness, to avoid prejudice, right? There are many data like studies on criminology which have some prejudice, but the prejudice is not because of the algorithm, it's because of the data. If the data has a bias, the model will have a bias also. And there's a very nice movement called Data Science for Social Good. This movement started in the University of Chicago. What they do is they have a summer work every year for 3 months when they go to a very poor country to try to use data science to solve some problem in the country, like water quality problem, public transportation problem, small economy, and so on. And this initiative spread out all over the world. And last year they had the first time in South America, which was in Chile. For now, I just quickly go how much time I have. I have 10 minutes? Right, 10 minutes. So I just quickly go some applications we did, particularly molecular biology related applications in São Carlos. We have used machine learning data science to try to improve genetic of cattle. This was made with the Embrapa Pecuária in São Carlos. We do lots of work in special analysis, mainly for cancer research. We have a collaboration with the Cancer Hospital in Barreto, São Paulo. I work some gene interaction for aging to see which protein or which gene can be associated with aging. Those can have some drugs that can delay aging. You have discrimination of long non-code RNAs, feature structure of microRNAs, prediction of plant product deposition, prediction of or cellular localization of proteins. We work with the body of drugs as well. Protein function prediction, protein-protein interaction, and now we are classification of CRISPR-Cas systems using machine learning. So I just quickly mention 2 of the works. The first work we did was in 2001, so almost 20 years ago. It was with Unesp Jabuticabal, and the idea is to investigate the effects of phosphorus foliar fertilization on guava trees. So guava is a very common tree in Brazil. So we want to predict the response to phosphorus application by try to predict the amount of phosphorus in the leaves and in the soil. And for that, you use artificial neural networks. In São Carlos, we have a center for called CEPID, is a FAPES center for research. It's an 11 years project, and this center is particular for transfer knowledge from computing, mathematics, statistics to government, to companies, to other universities as well, and you have some competitions every year. And one of the competitions have data from rising to predict fault in plantation of sugarcane. Of course, the productivity of a sugarcane of any plantation depends on several aspects, like the quality of the soil, wind, rainfall, temperature of the crops that are going to be planted, and so on. So the idea in this project, in this kind of competition, it was 1 year competition, was to use machine learning for regression for classification to predict what are the percentage of yield gaps and where you should plant or not plant in a particular area. And for that, use machine learning. And use some explainable models to see the importance of each variable for the prediction. And so that's just going back. Why do I mention before that Pagé work with explainable AI? So I just briefly talked about neural networks, but not only of neural networks. Most machine learning techniques, they produce models that can be black box or white box. Black box is when you cannot understand or interpret what the model is doing when you make decision. White box when it's clear how the decision-making process is happening. And in between, we have gray boxes, which are interpretable but not as interpretable as the white box models. As I mentioned before, there are very strong movement towards the use of explainable models. And even if you use deep networks, deep learning, you can always explain the model by several different approaches. So this is a tool that we did, using explainable models to predict whether to plant or not, using data from sensors. And another work we did is based on a work we do associated with glass production. we have a collaboration with Federal University of São Carlos to predict the property of glasses. So we have the molecular equation for the glass, and want to predict some properties like how strong the glass is if I just leave the glass to fall in the floor, for example. And we are doing all the opposite, because there are many different combinations of glass that never tried before. So what we want to try to do now is, someone wants a glass with some particular properties. So what should I mix to get this glass? And I try to do the same with agriculture. So someone wants to have this productivity in a particular area. So how should I mix? Consider that some variables are fixed to have a higher chance to have this productivity, to have a kind of a trade-off between cost and amount of plants I'm going to produce. So this is a tool called Alchemist. So I put what I want, what is fixed, and trying to find out, to have some suggestions about some variables to improve the productivity of the plant, of the plantation. We also do lots of work in gene expression analysis, but here is mainly for medical purpose, for cancer disease. We use AutoML to predict what's the best classification algorithm for predict cancer, for example. This is a very simple work. So we use several machine learning techniques with several data sets to create a meta-knowledge. And what we did is you found out for particular technologies, like you differ between RNA-seq, microRNA-seq, microarray, what's the best algorithm for a particular data set. And you saw that for most of the case, for example, microarray is better to use random forest, and for in some cases it's better to use random forest, in other cases it's better to use support to vector machines, and so on. You also do the same with clustering, but now we have a different purpose. When you do clustering, you want to find groups of data who have similar properties. But you may have some overlapping groups, for example. Look at this data. So it's gene expression data from 3 genes, which from different conditions, they vary at the expression level. So it's not easy to find the groups in this data. But if I can do clustering in 2 dimensions, in the variable dimension and object dimension, which is called big clustering, so I can find the clusters now. Right? So I just select which variables I'm going to use, which object I'm going to use. We all do work with some protein function prediction. Right? Protein function is a classification task that's very challenging because the class form hierarchy, and a function in a protein can have more than one function at the same time. So that's what's called multi-label classification and hierarchy classification. So this is an example of multi-label classification, where one object can have more than one class at the same time. And this is hierarchy classification, and the class can have a hierarchy. So I have to predict which point in the hierarchy are the functions that are associated with this particular protein. So this I'm working multi-label hierarchy classification. Right? This is how I model the data. You work with gene protein coupled receptors. I know that is not as common in plant as it is in animals. And for that, use a set of neural networks, like a deep learning neural network, with backpropagation. And this use the Funkat taxonomy to associate the functions to the protein, with a hierarchy in multi-label as well. And what it is very simple. It use a cascade of neural networks for each level of the hierarchy. And for each level, I could predict the class of more than one function for the protein. So we start with very simple architecture. It's called 8MC LMP, and then where the input of each network was the output of the previous network, and the hidden layer of the previous network as well. And then you have a new version which improves the results, where I also use the original input. How am the timing? Okay. So that's what I want to show you. First, I want to show what's the relation between big data, data science, artificial intelligence, and particular artificial intelligence, data science, which are more associated with extract knowledge from data. We have this glue that's machine learning. And if you use machine learning from end to end, it involves the whole process of data science. Then I told about the different possibilities of techniques you can use for data science and for end-to-end machine learning. So how can you select the best techniques, the best 6 of techniques? And I said that a recent approach is using automated machine learning or automated data science. We're trying to automate the whole process. The idea is not to substitute the specialists, it's to give some support for someone who's not a specialist, so democratize the use of artificial intelligence and speed up and avoid some manual, boring work for the specialists as well. Then I talk about social responsibilities when I use data science, like privacy, transparency, reproducibility, fairness, and so on, which are more and more important whenever you use data science, artificial intelligence, machine learning. And finally, I show some briefly mention initiative, University of Chicago, to use data science for social good, and I show some very simple applications of data science techniques in molecular biology, for example. So that's all. Thank you very much.
Thank you, Dr. André, for a great presentation. We are open for questions since the beginning of the speak, but if you have any question. All right, I have one.
Please.
You talk about gene expression, and gene expression data are usually very specific, right?
Yes.
So if I train a model for this data, how can I expand this for other data? Like, is common experience a kind of overfitting in gene expression data or something like that?
Yeah, okay, but what you can do some techniques like stopping or validation to try to avoid overfitting. But what I did in this particular experiment is, suppose you have 1,000 data sets for gene expression data. And then I took 900 of them, applying different machine learning techniques to this data. And then what I have now, I have these 900 data sets, and I have the performance of all different machine learning algorithms to these data sets. And then I use the machine learning, again, I apply machine learning algorithm to this data set to try to have a recommender. To say, whenever we have a new data set, I can suggest you predict what would be a ranking of the best algorithms to use for this new data set. And of course, nothing's perfect. The idea is to improve the results. But you can never say, that, no, this will get the best possible result. No. And the idea is just to improve the performance you have in the end, the model you have in the end.
Thank you.
Dr. André, thanks for the presentation. And I would like to know your opinion in a topic regarding the use of the machine learning models to make decisions. So let's say that you have a model implemented to make decisions, and how you think that this can in the future, the new training set will have decisions using these machine learning decisions, how you think that this can impact the future decisions, and if you think that somehow can have any negative impact, how you should manage these challenges?
Yeah. It can have, always can have some negative and positive impacts. In some countries, it's allowed now to have a machine learning, a model generated by machine learning to make medical diagnosis. But I think that some critical applications, like medical diagnosis, should have also the specialists together. So the idea is, you could use machine learning to try to reduce the number of people, to have a pre-trial. And if that's the case, it's very simple, and there is no kind of very grave consequence, then you can use the model. But if the consequence can be very difficult. For example, in medical doctors now in a hospital, sometimes they have to make decisions between some patients, and one of them is going to die. Which one should I treat? It's very common in in urgent hospitals. And what they do usually, they treat the person who has more chance to survive, or the younger person. That's what they do, right? So someone is deciding already. What's the best decision? By the person, by the machine, or by the two together? It's a difficult question. I don't have the answer. Another common application for education, for example. You can use machine learning techniques to suggest a personalized education for every person, or a personalized drug to every person. What's the best medicine for this particular disease for this particular person? I think you need always to have the supervision of a human being. So try to see the trade-off.
Andre, congratulations on your presentation.
Thank you.
So I work a lot on more the G by E by M thing, you know, the interactions that explain crop yield, for example, especially in the management part. And even though you talked about big data and everyone talks about it, I don't know, for me it seems that it is still very hard to really get the hands into this data, especially when it comes to the management part of it, like how the farmers are really growing and things like that. So do you have any experience on that? How, I think you mentioned Heising, how easy is that to approach like this kind of groups and get this data? Do they have them? They are willing to share?
Yeah, it's difficult because I think you're coming to the time where for some companies, some farms, the data has more value than the farm. And for them, they are very skeptical about giving the data. Because the competitors can see some process they are using. We had a collaboration with a company who were making juice. And you ask for the data. And they said no, because then you see how the process you are using to filter the impurity from the water, and then you can have some fees from the state government, for example. So the thing is, the data is valued so much. If you see now, the value of the companies, most of the companies have big value are companies based on data, like Google, even Apple has computed, but has lots of data as well, Microsoft. So for them, as I mentioned before, data, if not now, but in the near future, it will be more worth than all the land they have. That's why they are skeptical about giving the data. But there are some ways to give the data, like you can anonymize some variables, for example. People do it when they're trying to use machine learning to avoid prejudice. So they use cryptography sometimes to code some of the data. But because they can benefit as well, if you can have some good management advice for them using the data. So you have to find a kind of a balance. Okay, data is important, has a value, but if you extract them, if your data is just there, there's no value. You have to extract the models, knowledge from the data.
Hi, Andrea. Thank you for your letter.
Thank you.
I want to know how to apply machine learning in CRISPR, what algorithms do you use in that, and how to avoid issues in this data set.
Yeah. Well, this work of CRISPR is a collaboration with Freiburg. You just submit the paper, and you just, can I give you answer in a few weeks? Because if I give them, they can be very mad with me, because I said how you did. Give me a few weeks, send me an email, and I said you give the paper. And I'll tell you all the details, I'll describe everything. And even the code will be available as well.